All right. The integral test. Okay. What you need to make sure on this integral test is first you need to make sure that the functions continuous, positive functions, always decreasing, and you need to let the series or the sequence become the function of the integer. Okay? And the series will be converged if the integral converge. Okay? So to solve this integrations, you need to review a little bit about the improper integral. Okay? When you have the, for example, this one having the infinite endpoint. Okay? And then you might have these conclusions. Okay? Now, this is example. Now, from this integral test, let me add another image. Let me check the image. Okay. Now, if we look on the approximations from this graph, okay. If we imagine this is our functions, and if we evaluate area under the curve with the rectangles like this, okay, you will see that it has a gap, right? It has a gap. So actually, there will be a difference between the whole area and the rectangles, right? Okay. So we can take the gap, okay? So the gap, or we say the error, okay? The error in approximations, or we say it's called the Rn, or the remainder. So remainder is an error, and it is defined as the difference between the total sum minus the Sn. And of course, the notation should be the same, that the function should be decreasing on, let's say, from some n to the infinite point. And then we will see that the remainder, that is an plus 1 plus, maybe it's confusing, maybe n plus 1, or like that, an plus 2 plus this should be less equal of the integrations. Okay, so that means that it says that it should have some gap, or it should be less than the area, the total area under the curve. And of course, the other case that we might have is we can have the area that is overestimate, right? Overestimate. So this will be the remainder, n plus 1 plus n plus 2 plus Now, from these two cases, okay, we can have our conclusions. Okay, at least what is remainder? What is the limit of the remainder? Okay. So suppose write using k for the integer. F is continuous function, positive, decreasing for x greater equal n, and the sum of an is convergent if remainder is equal s minus sn. Then the conclusions is less equal Rn, and then less equal yes.
Can we turn off the light in the front?
Oh yeah, it's too bright, right? So this is the first inequality that represent the error, okay, the error. So it can work two ways. Okay. First, if you have some goals, okay, that maybe your goals is you want to make some calculations in maybe 0.01 error or percent error. Okay. You want that calculation. So you take that as your restrictions, and you make sure that when you have the functions or you have some factors that you want to calculate, maybe you want to know how many times you need to work on, how many terms of the series. Okay? So you can get how many terms, how many iterations the process should be. You work with the some software, some simulations. That is how it actually works. Okay? We can set up the error first, or we set up the calculations and then we found out, oh, we have this error. Okay? So you can set up two methods. You can find the error, or you find the terms to match up with your goals. Your goals. Like maybe you want to have like 0.0005, and then you want to put into the calculations, and we have this inequality. Okay. And of course, working with this remainder and iterations means that at least you need to have some tools, okay? At least calculator, okay? At least calculator. Maybe I will show you like an example on how we can use this this inequality in a study case. Okay, study case. Let me go to next slide. Okay, if you have sum of the series 1 over n cubed, okay. So approximate the series by using the first 10 terms, meaning you need to have n up until 10. Okay. Estimate the error involved. Maybe that's the first question. So first, if you look the series, we can start by define the functions by 1 over x cubed, right? And of course, this is satisfy integral test, right? We need to set up this statement. We need to set up the function need to be continuous, decreasing positive functions. Okay, so satisfy the integral test, and then we can set up the series by taking the partial sum with n equal 10, so s 10. Okay, so we can set up some calculations. Up until 10, the first 10 terms. Okay, and then you will get some numbers here from your calculators. This is probably equal 1.1975. And then you check the integral test, which involve the improper integral, right? So we check the integral. I hope you still remember if you have this improper, meaning you need to use limit for the infinite interval. Okay, and we set up the integral. That is, this will become negative plus 1 negative, right? So 1 2x squared from n to t, and then we set up calculations, limit as t approaching infinity, and from here we get that the 1 over t squared will be 0, right? Okay, so this will equal to 1 over 2n squared. So by integral test, we get the results of this integral is 1 over 2n squared. Okay, so we have two approaches. First approach is using the partial sums. The second approach, the integral. And what we are going to do is we just compare both. Okay. So, meaning the first 10 terms, meaning we use n equal 10 here, and then we can compare this number to that number. So, Rn should be less equal of 10 dx, or we get the 1 over 2 and then 10 squared, or this is 1 over 200. And then we say that we can say the error size is at most, or we can just write error size equal to 0.005. Okay, that's the first questions. Okay, so we get the error size is 0.005. The other type of question, I will go elaborate this more. If you want to have maybe if wanted accuracy, meaning it's the error or the remainder. Let's add more zero. So this is what we want. So means need to find n such Rn is less equal 0.0005. Okay, and then since we have established this, that is equal with the 1/2n squared, we may have relations directly we can write. Okay, and then from here we can find that the n squared should be greater than 1, or it should be greater than 0, or n should be greater than square root of 1000, or this is equal 31.6. And we can conclude that at least let me take this resize a little bit. Okay. So at least 32 terms to have accuracy 0.0005. So it's either you find the error or you find how many terms to get to that error. Okay. Okay. Okay, let me change the slide. Okay, let me just works on, this is the remainder. Okay, and you have this inequality. Right, and then if we add adding Sn, okay, meaning if adding Sn means that the Rn is, or Rn plus Sn is equal S, right? So if we add adding Sn to this equations, the inequality, this will become Sn plus less equal Rn become S, and this is less equal Sn plus, and we can also use this inequality to check and compare. Okay. And the way it works is practically the same as just Rn. And that's the integral test and approximations, or finding errors. Okay. So we can approach with these two methods to approximate the sum and also finding the remainder, or the error, okay. The difference between the total sum and the partial sum. Okay, now, so this is 11.3. Now 11.4, we still in how to test the series. We have, it's called the comparison test. Okay, let's consider the series. Let's consider this series. Okay. We know from the introduction of the series that this is the geometric, right? The geometric series, or we have also visualized in terms of the Zeno paradox, right? 1 over 2 with power of n half plus 1 over 4 plus 1 over 8 and so on. And we know that this will be converged, right? This will be converged from geometric series. So we know that this is sum of geo series, and we know that this is converged or convergent. Okay. Now, if we have another series, okay, let's say we have a series that is 1 over, we modify a little bit, 1 over 2 with power of n plus 1. Okay. Of course, from what we have compared before, that this series or the sequence itself, if we compare both pattern, this will be less than the right one, right? And since this is the series converge, this also makes sense that the series here should be converged, right? Should be converged also, right? There's some proof, but I think we will look a little bit later. But in this sense, what I want to say is we can have a direct comparison test. That suppose we have two series, AN and BN. Both series with positive terms. If the series BN convergent, and AN is less equal BN for all n, then the series of AN also convergent. And the second case, if the BN diverge or divergent and AN is greater equal BN for all n, then the series AN also divergent. So we need to observe, evaluate whether AN is greater than BN or AN is less than BN. And I think it's quite logic. Like if you see that this BN is already smaller than AN and BN is already diverged, of course the series that is greater than BN should be also diverged, right? But you need to be careful. You need to be careful. If this is less, well, it's not necessarily true. Not necessarily true. So you need to check if it is the first case or the second case. So in practical, how do we use this two method? First, if you have the series, and the series is just, the question is just asking whether it is converge or diverge, not necessary to find the value. You can think any series that maybe you think that you can find that, oh, maybe I'm using the series and then compare, and you can find whether it's the first one or the second one. Then you can take that method and you can determine whether the series that you want to find is converged or divergent, just by comparing the two series. So I think because we have learned some terms that like for example the geometric terms or the harmonic series that you already learned before, that you should know that whether it's converged or diverged, we can use that to compare with the one that being asked, the one that being asked for. So let me just give you a slight example on how we can use this direct comparison test, okay, in more practical. So example, you have sum okay. So you need to find whether it's diverge or converge. Okay. Now it looks the pattern seems that maybe a little bit complex, or if you think you need to use integrations and maybe it's too complicated. But if the question is just asking diverge or converge, then we can use the comparison. We can use the comparison. Okay. How do we use the comparison? And in practical, you see that this has 5 over 2n squared plus 4n plus 3. So we can make up a series that maybe we can evaluate easily. We can evaluate easily. So perhaps we can start with, we have 5, we have 2n squared, and this is the highest polynomials, right? The highest polynomial. Well, we can think of 5 over 2n squared, which is maybe we can take this and we can think of a series that has 1 over n squared. And we know that if we have this is less than this, right? And we know that this is converged, right? From the improper integral, we still have some from the P, right? The P test, or in our case here is called also the P series. That should be a converge, right? So whenever you have 1 over n with P, and you have P is greater 1, it should be converged. And when you have P is less equal 1, it should be diverged. This is we have learned slightly in the improper integral for this P. We can also use it for the series also. Then we may write the series like this, and we know that this will having this conclusions, and we have concluded that this will be converges, and in conclusions the series also converge. Okay, one thing to note is this is practically from n equal 1, but or we can say it's true for all n starting from n equal 1 to infinite number. But in some cases, maybe we can have some verifications that maybe n will be true. This will be true when n is equal to some number. Okay, not all numbers like start from 1, maybe 2, maybe 3, depends on the functions. It depends on the function. Maybe if you check, like you check the number n equal 1, n equal 2, maybe at the very first few terms, maybe we cannot say that this is less. Maybe after maybe 4, then we can say, oh, this is change the inequality. Okay? But then after 4, it's become a constant. It's become clear that we need to set up that the n may be from 4, not from 1. That's also can be happening. Well, this case is, I think for this one, it's from n equal 1 is already true. Like if you have the ln k over k, and you want to check with the harmonic series, we know that this is diverged, right? But if we check from 1 is 0, right? ln 1 is 0. And then check with 2. ln 2 becomes ln 2. And compare with 1 over 2. Is it satisfy the previous method? I don't think so, right? But it starts from 3. It starts from 3. Then we can say that these terms will be true when k is from 3. Okay, that's what I meant before. So when you check 1, it's 0, it's less than this one. Right? But when you check from 3 and 4 and 5, it becomes sure that this will be greater. So you know that from here that this will be, the series will be diverges by direct comparison test, or you can write just comparison test is also fine. Okay, but there is some terms or some cases where we cannot really use this comparison test. For instance, if we have we want to try to evaluate this and comparing with, so consider this series. We know the series is convergent, but if we check the inequality, this is what happened. This is converged. This is greater than this, so we cannot really see the conclusions. If this is less, then we might have some conclusion. But this is something that might happen in your solutions. So that means we cannot use direct comparison test. Okay? We need to use another way. Okay? So another way is still it's comparison test, but we need to have another method. Okay, let me write here. Cannot use direct comparison test because it's not satisfying the case. Okay, the way we are using is it's called the limit comparison test. So suppose we have series AN and BN, both positive term. Now we have limit AN divided by BN and equals C, where C is a finite number and C is positive, then either both series converges or both diverges. Okay. So this is we call the limit comparison test. So we take the limit and then use the series AN and BN as a ratio. And when we have some constant, then it means that either both converge or both diverge. So it depends on the series that you're comparing with. Okay. So if, for example, AN is the one that you want to know, BN is the known series, you know BN is diverge. And when you have this, it means that both diverge. But when BN may be converged, then both converge. Okay, let me just add some notes, okay, to make this limit comparison test seems logic. So let m and small m positive numbers be positive numbers. So m less c less capital M. Okay, AN over BN is close to C for large integer n. There is integer capital N such that if we take the m less, we change C with AN over BN and less capital M. This is when the small n is greater than the integer n. Then we can have this statement also. We move out the BN to both sides. So if the series of BN converge, so does the series of Bn, and thus the An converge. Okay. If series Bn diverge, so does the series of the small m Bn, and the series of An becomes divergent. So meaning, if we can take this ratio using limit, and we take that and having close to C, which means we are using the limit, then we can have both series converge or both series will be divergent. And we can actually try to find whether this is converge or diverge using the limit comparison test. And we can use the, so consider Bn, and this will be An, okay? And we can check the limit. This is equal 1, right? And because of this is converge, and we have this is equal 1, which is this is greater than 0, then An also converge by limit comparison test. For example, if you have the result 0, then you don't have any conclusion. You need to have a positive number here, positive constant. You need to have C. You cannot have 0. Okay? I think it's way more practical than direct comparison test. Okay? It's way more practical. And sometimes you can use several methods to one series, and you can choose which method you find more suitable. But I think we can stop until here, and we will continue next week. Any questions? Okay. If there's no questions, so let's stop the